Now we will see some numerical problems related to the rectifiers. Now the first numerical is a 50 ohm load resistance is connected across a half wave rectifier. The input supply is 230 volts RMS at 50 Hz. So this is just like our power system in Pakistan. Determine the DC output average voltage peak to peak ripple in the output voltage VPP and the output frequency FR, ripple frequency. Now first we need to know that this is 230 volt, that is the RMS value, and if we need the peak value we will multiply it with the under root 2. So this is how the peak value has been determined. This is 325 volts. Now the output DC voltage that we have discussed earlier, that its formula earlier for the rectifiers, that is the DC formula for the half wave rectifier is VP over pi. So VP over pi it is 103.5 volts. Now the peak to peak ripple voltage, it is the difference between maximum and minimum in the V naught waveform. So the maximum is 325, minimum is 0 volt, therefore the VPP is 325.3 volts. Now the percentage ripple would be VPP divided by V average into 100, that would be 314%. The ripple frequency is at the supply frequency, that is the 50 Hz. So we know that the output frequency of the half wave rectifier is the same as the supply, but in the case of the full wave rectifier it is double. So our next problem comes here. This is the full wave rectifier, midpoint full wave rectifier with center dead transformer. Here in full wave rectifier the transformer has a turn ratio of 1:2. The transformer primary winding is connected across the AC source 230 volts and 50 Hz. The load resistance is 50 ohm. For this current from the DC output voltage peak to peak ripple in the output voltage and output ripple frequency. Now here the RMS value it is 460 volts. Okay, RMS value is RMS value of V2 and V3. It is the 230 volts. Peak value of this is the peak value. This is the previously we know that the 230 that is 460 because of the 1:2 of the transformer. So RMS value of V2 and V3. V2 is 230 volts. Peak value of V2 and V3 is multiplied by under root 2. It will be 325 volts. So the DC output voltage that will be 2 Vp over pi. 2 Vp over pi. 2 Vp, 2 multiplied by Vp over pi, double of the previous one. The peak to peak ripple voltage can be calculated as VPP is equal to V peak minus 0, that is 325.3 volts, and the ripple frequency will be 100 Hz, that is the double of the previous one. And the percentage ripple here it is calculated as VPP over V average into 100 volts into 100. So this is the percentage ripple. Again there will not be units of this value because it is the ratio of the two voltage quantities. Okay. Now this is the some performance parameters of the rectifiers, and we see this is the symbol of the transformer, this is the primary side and secondary side, and this is the general symbol for the rectifier. This rectification is being carried out here, and then we get a VL which is supplied to the load, and these are the some definitions. These parameters are needed to compare the performance among the different rectifier architectures. Ideal switches with zero commutation type, zero on resistance, and load itself is an ideal resistance. Commutation is the process by which we can turn off a thyristor. So the process of switching off a thyristor or SCR is known as commutation. We have discussed all these things previously. Vp is the primary side voltage, Vs is the secondary side voltage, and VL is the load voltage. Okay. Now these are the performance parameters. V is equal to IR, that is the Ohm's law, and if we know the voltage we can find the current by dividing the voltage with the resistance. So here wait, just wait a minute. Yes, this we missed earlier, that this is the average value formula, that VDC is 1 over time period, integrate the voltage over the time period, and this is the RMS value, root, mean and square value that we already discussed in detail in class. And then comes the form factor. This is a very important parameter, which is the ratio of RMS over average value. So RMS we find from this value, and DC value we find from this formula. So these two formulas we find the RMS and DC values, and then the ratio of VRMS over VDC is our form factor. From form factor we will determine many other parameters of interest, like we'll see further. Like this is the ripple factor. Ripple factor is another important parameter used to describe the quality of the rectification. It represents the smoothness of the voltage waveform at the output of the rectifier. Now if we simplify the formula, we get this formula. formula under root ff square minus 1. So this will be the first we will calculate the DC value, then average value, and then form factor, and then from form factor we will calculate the ripple factor, and from ripple factor we will calculate the efficiency. Efficiency is output over input. Output, that is the DC output, and AC input. So this is the efficiency. By solving these all formulas we get the one major formula, which is 1 over ff whole square. So this will be formula we need to remember, that for efficiency it will be 1 over ff into square. So this is how we will calculate further in numericals. So this is the transformer utilization factor. The parameter characterizes the ratio between the average power and the transformer secondary volt ampere rating. This characterizes the ratio between average output power and apparent power energized the system. So this is output DC divided by VA rating of the transformer. This is VA rating is on the secondary side. Here you can see that VA rating is equal to VSIS. This is secondary side RMS voltage and secondary side RMS current. Now this is the displacement factor. We already discussed that thing in the power factor side in the first lecture in the class, that displacement factor is cos of phi, and power factor is VSIS1 cos of phi over VSIS, total power, output true power over total power. So here by dividing voltage we will get cancel out. We will get IS1 over IS into cos of phi. IS1 is the RMS value of the fundamental component of the input current, fundamental component, and IS is the total current. And the crust factor will be ISP over I. This parameter defines the measure of the peak input current as compared with its RMS value, the crust factor CF. Now this is the formula. We can see that the average and RMS values are calculated. VDC is equal to Vm over pi. So this is for the half wave rectifier, and current will be calculated by dividing the voltage with the resistance. We already discussed these points in great detail in the class, so I'm not again describing this in great detail as we have already discussed this. Okay, this is the VRMS formula, Vm over 2, and I will be calculated by dividing voltage with the resistance. So these are the values we got here. Now the efficiency and transformer utilization factor. At efficiency we will calculate PDC over PAC. PDC is PDC IDC over VRMS IRMS. VDC IDC VRMS IRMS. We have these four values we put in this formula and we get the overall efficiency. That is, please note that it is 40.51% for the half wave rectifier. And then comes the TUF, the transformer utilization factor, that will be PDC over VA secondary side. So PDC IDC over VS into IS. So that will be our, here IS means the RMS value. So here it is we get 28.6% for the half wave rectifier. Okay, now comes the form factor, which is simply VRMS over VDC. We calculated earlier these things, and this is 1.57. Ripple factor is under root ff square minus 1. So this is 121%. And peak inverse voltage, we already discussed this in great detail in class. That is the maximum negative voltage which appears across the diodes. For the half wave rectifier it is the negative of this ply. So it is 155.56 volts. Okay. Now this is a simple revision of the previous things, that is the series RL circuit. In that case we have the voltage across the resistance and voltage across the inductance. So we know that the voltage leads in case of purely inductive case. So here we have the resistive vector and 90-degree inductive vector. So by vector head to tail we get this resultant voltage, and this will be Pythagorean theorem. Its magnitude will be calculated this value square plus this value square under the root. So this is from the Pythagorean theorem. We calculate V, and I will calculate IV over Z. Z is the total impedance of the circuit, R plus XL, JXL. So here XL is 60.39, so ZL will be 0 plus J 60.39 or angle 90 degree, and ZR will be 60 plus J0 or 60 angle 0. So Z total will be R plus JXL. So when adding these two things we get this by head to tail 85.0785 and 45.15. I will be calculated E divided by Z. E is 120 volts angle 0 and 85.078. So this is the magnitude. If we ignore the inductance here, then the inductance when the inductance is ignored, only resistance remains in the circuit, and 120 degree divided by 60 we get the current here. So these are two values which we obtain. Rectifiers for the now this is for the VDC formula we discussed this earlier, that is 2 Vp over pi for the full wave rectifier, and VL, that is the RMS value. This is Vs over under root 2. Vs over under root 2. Now form factor is calculated here. VL over VDC, which is 1.11. Eta is calculated, which is 1 over ff square, that is 0.81, and RF under root ff square minus 1. So this is the table comparing both the performance of both rectifiers. Half wave rectifier we have a form factor of 1.571, and full wave we have 1.11. Eta efficiency we have 40%, and for the full wave we have 80%. Please note that the 20% is wasted in the losses, or 19%. Ripple factor is 1.21, and the other is full wave, which has lesser ripple factor, which is more desired. So this was all about the numerical of the rectifiers. Hopefully you understood it very well, that this form factor is very much important in calculating the efficiency and ripple factor. The most important is you must know how to calculate the average value, then how to calculate the RMS value. So if you know these two things, then these two voltages, then you get the current you get by dividing this voltage with the resistance. And if you have the voltage and current, you can have power by multiplying these two things. So hopefully the solving numerical will be much easier for you in exams. So this is the table for the summarized table, that for the sine wave this is the RMS value, and this is the average rectified value 2a over pi, and this is the form factor. Similarly for the half wave rectified sine wave, full wave rectified sine wave, square wave, pulse wave, triangular wave, sawtooth wave, and Gaussian white noise. So these are the most popular waveforms in electrical engineering. So this is a table summarizing the major parameters RMS and average rectified value, and then the form factor. Thank you for listening.